then we can take it one step further. Instead of looking at just the equivalence point, what happens slowly as we titrate? That's what we're going to answer over here. So the final part of what we're looking at in Chapter 8 is the role of a buffer. So what is a buffer? In chemistry, a buffer is something that will resist a change in pH. And if you're thinking Le Chatelier's principle, you're absolutely correct. Buffers are based on Le Chatelier's principle of an equilibrium system wanting to resist that change. Let's first talk about what buffers are in real life and then move over to some of the chemistry examples. If a disease is spreading throughout the population, people will be asked to maintain a space buffer, maybe 6 feet around them. If someone comes into that space, you move back to maintain that 6-foot space buffer.
He doesn't know. He doesn't know. Oh, he's gonna pick up the. Oh, no! No, I missed it.
When you're downloading some type of movie or game or whatever else you're interacting with, it will say buffering, meaning that it's letting the content play at a certain resolution, it's downloading more, but there's a certain capacity it's holding on to make sure that you have a smooth playback. And as bandwidths increase, you see less and less of buffering, but you may see that if you live in a more remote area. We also see buffers with contact lenses. If you use a contact lens, you'll have a saline solution your contact lenses are stored in, and this ensures that the pH of your contact lens is always going to match up with your natural pH, so the contact lenses are comfortable to put in. Blood is another example of a natural buffer. The pH of your blood is slightly basic, and when that pH changes about 0.02, we start increasing the need to breathe. Breathing is triggered by the acidification of your blood, and the acidification of your blood in a very slight margin causes the hypothalamus to increase the rate of breathing so you can get rid of carbon dioxide, and you're able to increase the pH of your blood again, put it back and restore it to where it should be, putting it back to normal. In chemistry, we'll most often see that buffers are common derivatives of acetic acid and other biological acids, whether it be oxalic acid, which can be used for cleaning coffee machines, or if you have other acids like malic acid, which sometimes makes it onto the final exam as a question. The graph that we have here shows the process of titrating a weak acid with a strong base. The weak acid is in the Erlenmeyer at the bottom with a pH meter and phenolphthalein, and at the top we have the strong base. As the strong base is added to the weak acid, we notice there is a sharp increase in pH initially. The pH then levels off for a while, and then very quickly it rises up to close to the level of the base that's being added. Notice it's not uniform, and it's not strictly logarithmic either, as we'd expect from a pH scale. So we have some questions here about exactly what's going on. So first of all, this data was obtained from a lab we did in fall of 2017, and it is the titration of acetic acid with sodium hydroxide. This graph can be broken into 3 distinct parts, or 3 different regions. Our first region we have here is called the buffer region. It's our first region. Our second region is the equivalence point. And our third region is our basic solution approaching the asymptote of the sodium hydroxide that's being added to the solution. With the buffer region here, what we know is that there's a useful region here where we have a very slow rate of change. what we're able to do is we're able to take a line and we're able to find this straight line region roughly here. And in this region, we have an area where change is generally resisted. It's steeper before, it's steeper after. The middle of this range is the most useful part of the buffer capability of this acid, because it can absorb acid or it can absorb base, depending what's added to it. Now we're going to take a look at the buffer region from the perspective of a chemical equation. Bet you didn't see that coming. So, A is our buffer region. In our buffer region, we have acetic acid being in equilibrium with our acetate ion and our protons. This is important because if you are adding an acid to your buffer region, you are essentially adding protons, and the reaction will shift to the left. Conversely, if you're adding base, you are removing protons, the reaction will shift to the right to undo that change. So regardless of whether we're adding acid or removing protons by adding base, again, OH negative pairs up with that, they make water, and although the atoms are there, it's not present in the same form that's part of equilibrium. So regardless of whether we're adding acid or adding base, we have a system here that has the opportunity to move to the forward or in the reverse direction. And if we started right at this point here in the middle of our buffer region, we have quite a lot of capacity to absorb base without a significant change in pH, or absorb quite a lot of acid, again without a significant change in pH. Of course, the buffer region isn't perfect. There is going to be a slight amount of change, but it's not significant. Again, think of our contact lens example. The contact lens might have a little bit of evaporation, a tiny little bit of leakage as the water is absorbed by some of the seal, some of the materials that make up the container, and that little bit of water is absorbed, slight change in pH, the system undoes that change. Now let's discuss what's happening here from a Ka perspective. So we know that Ka is going to be the concentration of the acetate ions times the concentration of protons. No surprise here, exactly what we've seen before. Products over reactants every single time. Exactly the same thing. And if it looks repetitive, that means you're doing your work and understanding things. So we have our Ka expression here, our products over reactants, just like we've seen in the past. We also know that we're going to have a special interest in the middle of this buffer region. That's hugely important because in the middle of the buffer region, it can absorb base being added or it can absorb acid being added. So this is the optimal place for buffering from the perspective of ability. Now in the middle of the buffer region, we're halfway to our equivalence point, which is where our acid is neutralized. That means if we're halfway there, this equilibrium reaction has gone halfway to completion. If it's halfway to completion, this concentration, the acetic acid concentration, and the acetate ion concentration must be equal. Therefore, they would cancel out, if they're the same, in an equilibrium expression. This is absolutely fascinating, not only because I'm a chemistry teacher, but because this means that our Ka value in the middle of our buffer region is going to equal the proton concentration. Why do I care about that? Well, if you're doing a lab, which you're not, I'm sorry. If you're doing a lab, what you're able to do then is draw a line from the middle of the buffer region over to the side here. When you do that, assuming your line's straight, when you do that, what you end up with is an intersection point on this axis. And it's snapping and it's really annoying. Either way, what you end up is with an intersection point on the axis right here. That value is going to be the pH. So if we take the negative log of this whole equation here, we find out a new value called pKa exists, and it is the same as the pH, because the pH is the negative log of the hydrogen ion concentration. So pKa equals pH in the middle of this buffer region. We're taking the negative log of both sides. Why is this important? Well, this is hugely important because if we have a pKa value, we can also go in the reverse. So the students who completed this lab would have found the pH value. Let's change color in this one. The students who completed this lab would have found the middle of the buffer region here. They would have then found pH. Once they have pH, they can solve for pKa. pKa allows them to get the Ka, and now they've determined the Ka of acetic acid, which should be the 1.8 times 10 to the negative 5 value you've seen before. So it's an experimental way for us to determine the Ka of an acid, the same Ka we've been working through all the way through this unit. If you haven't done this already, add this to your notes and make sure you're comfortable with the connection between Ka, pKa, pH, and concentration of protons. The second part of our graph looks at B. B is the equivalence point. The equivalence point here is exactly what you would have expected to see. The amount of acid and the amount of base are the same. The whole thing is neutralized. We end up then with our equivalence point. Now in the previous part question, we saw that our equivalence point of pH 7 isn't actually pH 7. Our pH is quite a bit higher. Our pH is higher because the acetate ions that are floating around in solution, these acetate ions here, interact with the pure water and drive up the pH. So we never actually have the pH remaining at 7. It's about, it's just under 9 as we saw previously. So that's our equivalence point. Never really stops at 7, making titration very, very difficult if you're looking for that faint pink color we saw in grade 11. And finally, part C. With part C, we have a solution that's now essentially becoming the base. So we can say becoming the basic solution, sodium hydroxide. We've neutralized all of our acid. We have a little bit of acetate ion floating around, but really what we're approaching now is kind of an asymptote here where this is the pH of our basic solution and it's approaching that. It will never get to that line because we always have a little bit of salt water that's there, but this is leveling out as it's approaching that asymptote. So finally now, taking a zoomed out look at buffers, we see that buffers have a couple things in common with what we've seen in equilibrium. We know that buffers have a region where they use Le Chatelier's principle to resist pH change, either by absorbing protons or releasing protons into solution. They're only able to work to a certain point, at which point the buffer becomes overwhelmed and gives up. Much like you being surrounded by people, you have a personal space bubble, but if you're in a concert, that personal space bubble is gone. Just too many people close by and that disappears. Concentration increases, we zoom past the equivalence point, eventually level out. Finally, now make sure you've done the questions in the textbook for Chapter 8. All the blue examples at absolute minimum. You can expect a test on or quiz on this coming up in the near future. Check Google Classroom for any updates and things like that. Let me know where you're at, and good luck.